Okay, thank you for the introduction. This talk is about IMIX, hardware enforced in-process memory isolation. This is joint work with my colleagues at Technische Universität Darmstadt and is a result of a collaboration with the Intel Research Institute for Collaborative, Autonomous and Resilient Systems. So, what's the current state of art? Currently, an application is maybe hardened against software attacks and has a so-called mitigation that changes the code to protect it. And this also includes a safe region of the mitigation where all the mitigation secrets are stored to protect the app code. However, if an attacker manages to corrupt the app code, for most of the isolation techniques, the attacker is able to attack the mitigation safe region itself. What we want to propose with IMIX is a deterministic isolation primitive that can be used to lay the foundation of really secure mitigations for code. So, first question is, why is in-process memory isolation actually a good idea? Why do we want to have it? Yeah, as all of you might know, we already have inter-process isolation enforced by the operating system, which means that every process that is running on your PC is actually shielded from the other processes using virtual memory. But as I explained, there is no actual in-process isolation. An attacker that corrupted the code can further corrupt the memory and then gain complete control over the application if there's a single vulnerability with a read-write primitive on memory. So what we need to fix this is some kind of isolation. Just as a small example, there is a very popular mitigation technique called shadow stacks. And what a shadow stack basically does is it backups all the return addresses from the stack to its safe region and restores these return addresses once you have a return from a function. This works like this. So we could fix the attacker's malicious input. But as you can see, the shadow stack space address is randomized. This is usually stored in a register, so it's safe from attackers. However, a single information leak may imply that the attacker can now modify this shadow stack and just overwrite the backup instead of the original return address and still gain full control over the application. So our contribution to this is we introduce a new memory isolation primitive that we designed to be, or to protect the whole pipeline from compiling down to the hardware, and evaluated this based on our proof of concept implementation with compiler support as well as a use case for mitigation to use, and evaluated this especially under the assumption that this mitigation makes heavy frequent switching between the different compartments that we isolate. So what do we have currently as existing work that can probably also do this? Recently, there was a lot of media coverage about memory protection keys because Intel finally brought it to x86 processors, to their x86 processors. Memory protection keys allow to define up to 16 memory compartments where you can define the permissions for each of them. However, setting these permissions requires that you, for every switch of the domain that you want to do, reset these permissions. And this limits its use case in high-frequency switching. So what else do we have? We have hardware bounce checking by now. So you can, for example, for a buffer overflow, prevent this by using hardware bounce checking instead of software. We can use this for a two-sided check and see how far an isolation region goes. And we have good old randomization, but as I told you, there might be problems. For hardware bounds checking, this incurs even more overhead because you have to do excessive instrumentation to perform to get this, which leads to a high performance overhead. Whereas, as I told you, randomization has entropy-based problems. So if you guess a single information, then it's basically broken. So real question would be, what characteristics should a memory isolation primitive have today so we can use it to fix our software? Most important, we want some kind of policy-based isolation. So a developer or a mitigation developer can have his own policy, which memory should be divided and to whom it may be accessible. And this is especially true, for example, if you have an application with several threads and you want them to be shielded against other threads. Most certainly you want to have a hardware enforced primitive because this reduces your attack surface from an attack on the whole isolation mechanism down to only configuration attacks that you can perform on this isolation. And as I told you, you want fast interleaved access to switch between those isolated regions. And most important, because we still carry our legacy, you want this to be fail-safe. So if you have a linked library in your application, you don't want to have this library access your sensitive data. So this should default to an error. So what's the current state of art in memory isolation? We got software fault isolation. Previous speaker mentioned this, which is pure software most of the time. We were used to have segmentation, which we don't have anymore. And sorry for this, but I think it won't come back. So this is mainly done for space reasons in the chip itself. As I told you, we have randomization in form of memory hiding. We can use extended page tables to have more control over permissions. We have MPK. We can use SGX to hide our data, but maybe there are also attacks on this. And of course, SGX is rather slow to switch in and out. And MPX. And most recently, we have Intel CET, so control flow enforcement technology, which basically does exactly what I suggested in the first part. It, next to its CFI label support, it has a built-in support for the shadow stack. So there is a safe region in hardware where the shadow stack is located, and you have dedicated primitives that you can use to access this shadow stack. So you have some kind of secure push and pop. So looking at all those existing primitives, our goal was actually build a primitive that incorporates all of the interesting aspects. So we came up with IMIX. IMIX is a hardware-enforced in-process memory isolation, which we designed to be at page granularity. And it supports two separate isolation reams because we found that enough to support most of the mitigations because they only need one save region. And you can still have the other regular memory domain. And most important, this has the benefit that we don't need to check permissions for each of the domains. We only have two, and we can encode that information in a special instruction. We made this the SMOV instruction, which can be used for a secure move to this respective shielded memory area. And we got the regular move instructions, which can access regular memory. This allows us to next, for example, for write or execute memory that we have for code, provide a similar guarantee for memory, at least for the sensitive data. Compared to the related work, we bring policy-based isolation because we can prevent other threats from entering or accessing the main thread's sensitive data. We have this hardware-enforced support, fast interleaved access, and we can also prevent legacy libraries from accessing this sensitive data because they don't have access to this small instruction. So how does it look like for our use case with shadow stack? We still have the information leak. The attacker knows now where the shadow stack is located. But if the attacker tries to overwrite that return address in the backup, he only has access to a move instruction. For example, this could be a simple buffer overflow, which is usually a loop, and you just move all the data. So you can assume that there is a move instruction is accessible. And so the save region of the shadow stack can't be overwritten. Nevertheless, we have this smooth instruction that can back up or restore return addresses from the shadow stack, like Intel CET, but more general. How did we implement this? First, we have a SMOF-based load store representation for LLVM. We did this for the intermediate representation so that this can be used by LLVM passes as well as developers using attributes, and integrated this in our pipeline. Next to compiler support, where we can actually use that instruction in the binary, we have OS kernel as well as memory support. So we have to give this instruction a fine granularity at page table level. We use the page table bit to set a flag whether a memory domain is sensitive or not. This is unused previously. And we, of course, made changes to the OS kernel to support these page permissions, for example, for mmap or mprotect. Of course, you cannot make a hardware extension if you cannot modify hardware. So we implemented the SMOF instruction for the CPU core, as well as introducing this SMOF check to the MMU. This is analogous to the read or execute check, because, I mean, if you're writing memory and you see the NX bit, you won't let that pass, and this is quite similar to this. For our evaluation on this, we emulated the CPU part using the Intel simulation and analysis engine, which is some kind of JIT-featured emulator, and check this for feasibility. So is there any difference to a regular move in performance, in feasibility? And this is our complete pipeline. So you have a binary. That binary may contain move and smooth instructions to different regions, and we even considered a malicious case. So as I previously said, a regular move can write to normal memory or read from normal memory, whereas the smooth region or smooth instruction cannot read or write the normal memory. This is especially important to give a two-sided isolation on this. And of course, the smooth instruction can write or read to protected memory, whereas the move instruction cannot. And for our use case, we were looking for a mitigation that actually requires high frequency of switches for domains. And this was easy to find. We found a code point integrity by Kuznetsov et al. And CPI effectively prevents code reuse attacks by having a safe region that stores metadata about code pointers or indirect code pointers. And originally, this is hidden in the memory, and the base address is stored in a segment register that is otherwise unused. So you can guess that this randomization secret is probably secret. Nevertheless, Evans et al. Showed that this might be broken based on low entropy. So we wanted to have a deterministic isolation for this. This is how CPI works. So for CPI, you take a regular code pointer, move that with some metadata to the safe region, and restore it if necessary based on an indirect dereference. using the GS register. In the CPI paper itself, the authors evaluated different approaches for safe region protection. Originally, for 32-bit architectures, they used segmentation, and for 64-bit only randomization. For us, during the development process, this brought an important factor in that the implementation itself is highly modular on how to protect the safe region. So it was a very quick process to add support for this using IMIX. And what we've actually done is we changed all those register-based offset moves to direct memory accesses, because you can resolve all these addresses at compile time. And we got quite promising results, I would say. So CPI and segmentation means, this is the blue bar, by the way. This is the regular CPI using the segment register as a base register, where we have in orange our IMIX-based CPI, which is in most of the cases quite similar. Now note there is CPI and memory protection keys. We based this implementation on the approximation of the MEMS-entry paper, because during implementing this, MPK was not available in consumer variants of processors. And additionally, we evaluated MPX for CPI safe region protection for the two-sided case. So you check both bounds of the isolated region. As you can see, for the geometric mean, segmentation and IMIX are nearly identical, I would say, whereas the other solutions or induce a bit more of a performance overhead. So, as a first conclusion, IMIX is the first practical solution that does not need too much hardware in the processor for in-process memory isolation. We enforce this in-process memory isolation at page granularity to further leverage the existing functionality in the kernel. And all the existing related work cannot really be used for higher frequency switching in current mitigations. And we tackled this problem especially. Now, talking about conclusion, what is the way we could go with this? We thought about applying IMIX to the complete memory pipeline. So find a way to bring this to the caches, see how we can incorporate this to the TLB, or a similar technique to the TLB. And as we've seen with other hardware primitives, for example, the extended page tables, sometimes these hardware primitives allow a completely new way to design mitigations. So we can use extended page tables for execute-only memory. We can use memory protection keys for execute-only memory. Maybe this opens a whole new direction in mitigation research for us. And yeah, let's see. And to this, I end my talk, and thank you for your attention.
Hey, nice work. This is Hong from Georgia Tech. Can I have a comparison of MX and HDFI, the hardware-assisted data flow isolation?
Yes. We did not evaluate that, but in comparison to HDFI is for RISC-V, if I remember correctly. And HDFI uses a lot of hardware to prevent all this performance overhead incurred by their tagging table that they use for the memory. And this is already incorporated in the x86 hardware that we leverage for IMIX. So actually IMIX is for isolation, a kind of subset, but it doesn't require all the heavy hardware changes that HDFI requires.
I see. Okay.
Okay, thank you for your question.
Hey, so the S move sits in the code space of the target application you're trying to protect?
Yes.
So what's stopping me from using a gadget to just S move
Yeah.
into the stack?
Yeah. Important to note is that this is a hardware primitive for mitigations. So best case would be the mitigation stops you from doing this.
So there's another function that prevents the S move from writing to your stack in the context of the application?
No, like this. You got CPI in place, which prevents code reuse. And CPI protects its save region using the smorph instruction. So you as an attacker have only a read-write memory primitive, but you cannot attack this save region, thus you cannot perform code reuse.
Okay, so you're banking on the fact that you have CFI protection.
Yes, CFI, CPI, yes.
Sure.
Okay,
Thanks.
thank you.
Really nice work. I see you're very comprehensive. When you were looking at the 32-bit stacks, I mean the segments, did you also look at the ring structure as well in your evaluation?
Can you please repeat the last part of the sentence? Did I look?
You looked at the 32-bit segments on the x86 processor.
Yeah.
Along with that, did you look at the ring structure as well in consideration for this?
Ring structure?
Yes. 32-bit. We have 4 rings in the x86 processor. When I finished watching this whole thing, I said, "Gosh, you just justified the use of rings." And to give you a little bit of overview, the segments are actually keyed to a ring, so you can have multiple segments in one segment, various segments begin various rings, and for the application, depending on how you set up the processor, you can have up to like 3 rings for the application, so it provides a nice handy way of segmenting the application. They're still there in 64-bit mode. Unfortunately, they're not really there in 64-bit mode. It's like the segments are sort of there, but it's like a hand wave.
Yeah, but based on the fact that Intel is trying to reduce segmentation functionality, maybe we should.
Yeah, but what's happening is everybody's saying, "Hey, they come down with poor man segments." And so actually, there's been a lot more justification of segments in the past couple of years than I think Intel's gotten surprised by that. But I just was wondering if you continue evaluation, please look at rings.
Okay, yeah, this would be interesting. Maybe we can have a chat later.
Okay.
Thanks you.
All right, let's thank the speaker one more time.